Okay, so today we will discuss one paper in Neurip 2017, Beyond Parity, Fairness Objectives for Gravity Filtering. So before we go into the details of the paper, let's discuss a little bit about bias in recommended systems. So what is bias in recommended system? In one of the keynote in the Rexis conference 2020, Dr. Ricardo lists out three types of bias that may occur. The first type is statistical, where we actually have some prior distribution and actually we have a significant deviation from that prior distribution. But I mean, this prior distribution most of the time is unknown. So that could be one type of bias. Another one is cultural, where we actually have interpretation and judgment phenomena acquired throughout life. So different people have different bias based on their culture. Another one is cognitive, which is a systematic pattern of deviation from norm or rationality in judgment. So he listed these three types of bias that is we could use to actually explain why we have a different bias. And some source of biases, here are a few kind of attributes, right? We can look at to see where the bias come from, like gender, racial, sexual, age, religious, social, linguistic, geographic, political, educational, economic, and technological. In this paper, we actually focus on two specific type of bias. The imbalance in the population within the system. So we talk about population here is the population of users. So we have different group of users, and they have different population. That is a bias that might actually influence the unfair recommendations that learn from the system. Another bias is observation bias, where a certain type of user have different tendency to rate different types of items. This second type of bias actually related to the feedback loop of the system. So if the user is not accommodated by a particular item, they're not going to have chance to actually rate the item. So you actually have lesser chance to actually see that user rate that particular item. And over time, that feedback loop of the system and the user feedback reinforce that bias with observation. So these are the two types of bias that this paper focused on. And actually, they try to address these two biases to make a fairer recommendations. Throughout of this paper, they use first data set is the synthetic data. So let me discuss a little bit on the synthetic data, how they actually create this synthetic data set, so that we can actually better understand why they derive the methods later. Let's suppose that we have the problem of recommending education courses for 4 group of users. Let's say we have 4 group of users. The women who actually enjoy the STEM course. The STEM is science, technology, engineering, and mathematics, right? So we denote this group as W as the women who do not enjoy STEM, which is W only. And similarly for the men, we have MS and M. To simulate the rating matrix or the interaction matrix between the users and the items, we first have this metric. So this first block actually represent the probability how each group of user gonna rate positively to the group of courses. Let's say we have 3 group of courses: the feminine courses, the STEM courses, and the masculine courses. And let's say W and feminine 0.8, meaning the user belong to the group of women gonna have 0.8 chance giving the positive rating to the courses in the feminine group courses. And similarly for the STEM and the masculine. So this stochastic block, we're gonna sample the rating from this stochastic block. The second block is the probability that that particular rating will be observed. So because most of the time we see that our rating metrics are missing, right? A lot of missing values. So this plot gonna control whether we observe, the system observe the rating that being drawn from the first plot. So that second plot gonna determine that probability. And okay, so this paper focus on very traditional approach to recommendation, which is metric factorization. It's very successful approach for building recommendation system. And just a little bit background on metric factorization for some of you that is not familiar with the approach. So we actually have the rating matrix between the user and items. And we have a lot of missing values there, right? So this very big matrix, like a million of users, thousand of items, a few 100,000 of items, we can actually approximate this matrix with two other lower ranked matrix, the P and the Q. So the P, we can call it as the metric of user factors, and the Q is metric of item factors. And the dimension of the P and the Q, the D there represent the other dimension of the P and the Q. That is very low dimensions as compared to the dimensions of the original rating matrix. So a couple of intuitions why we can actually approximate this very huge matrix with these two low dimensional matrix. So in the psychology point of view, right, we have so many humans on Earth, like billions of humans, but people are not very different. So we actually can narrow down them to like a few hundred groups of preferences, and people in the same group tend to have like similar behavior, similar preferences. So that is one of the reasons why we can approximate with the lower rank. And another one is that we have a lot of missing values on the original matrix. So using low rank approximation also actually have a regularization effect, where if we have a higher rank, then we have a lot of free parameters, then we are easier to be overfit on the, when we're actually trying to approximate the big matrix, the rating matrix there. So below I show the, so each of the rating in the original matrix is being approximated. The Y, IJ there, IJ are the subgroup of the location of the entity, the entry in the original matrix, being the inner product between the two vectors in the matrix P and the matrix Q. And below is the loss function that we are trying to minimize. The first part, the lambda there, is the regularization, where the second part is the reconstruction error, the square loss that we're familiar with. The Rij are the original value, and the Yij are the approximated value. So this paper proposed, actually they focus on 5, but they propose 4. The first 4 metrics are proposed by this paper. The last one is proposed by the others. So actually they're trying to compare these 5 fairness metrics for the recommendation problem. First one is value unfairness, absolute unfairness, underestimation and overestimation unfairness. And the last one is non-parity unfairness. So we will walk through these 5 different metrics to see how it actually trying to capture. So I just introduced how they actually generate the synthetic data right earlier. So let's suppose that we have a 2 group of advantage and disadvantaged user. So in this case of the cost recommendation, let's suppose that the men are the one who have advantage and the women are the one that have disadvantage. And the first value unfairness, this metric will see, we measure the inconsistency in the side estimation error between the 2 groups. So the N there is the number of items. So for every item, we see the average prediction. The E, G, Y there is the average predictions of the model for the first group, for the man. The EGR there is the true average rating for that particular group. So we see the difference, right, the error between the two. The second one is the same as for the other group. So we gonna see the difference with the true rating, and then we see what is the difference between the two groups. So look at this one, right? This value actually high when the side estimation are actually different. So let's say the first group we have like a positive value, whereas the other one have the negative values. Then we have a big number, right? And the other way around. When the first one is negative, the other one is positive, then we have a big value. So this unfairness occur when one class of user is consistently given higher or lower predictions than the other. So, so for example, in the course recommender system that we have, the value unfairness manifests the male students being recommended STEM courses when they are not, even when they are not interested in the STEM courses, and the female student not being recommended STEM courses if they are, I mean, they are not, they are interested in the STEM courses, but they are not being recommended the STEM courses. The second metric is the absolute unfairness. This is a little bit less strict than the previous one. So this only care about the inconsistency in the absolute estimation error. So you only care about the absolute error. You don't care about the size. And this one focus on the quality of the prediction of each user type. So they actually only care that if one user type have a small reconstruction error and the other user type have a large reconstruction error. So one type of user have the unfair advantage of good recommendation, where the other has a worse recommendation. This is how the absolute unfairness measure. The next one is the underestimation unfairness. So this one only measure the inconsistency in the underestimation error. So it's okay to overestimate, but it's not okay to underestimate the ratings. So as long as your estimation is underestimate the true rating values, it will incur the cost. You see the function that the max within 0 of the true rating minus the estimation, right? So if the estimation is smaller than the true ratings, then you have the cost there. And this actually emphasizes that some missing recommendations are more critical than extra recommendations. So it's okay to recommend more courses, but it's not good to actually miss out some of the important courses. This is very similar to the recall metric that we usually measure. Similarly, we have the overestimation unfairness, where we actually just flip the side. And for this one, it's emphasized on providing many recommendations is actually harmful. So we don't want user to be overwhelmed by a lot of recommendations. So we want to recommend less number of recommendations, but it's correct. So this is similar to precision, actually focus on precision. So just an example that is actually we don't want different group of user have some of the user have to spend more time to actually look out for the course that they want. The very last one is a non-priority unfairness. This one actually so the difference here is what? It's actually this one don't measure for individual item. They just average overall, and they just see that actually the system is kind of being fair between the two groups across the set of items. And this actually been introduced much earlier in the ICDM conference in 2011. And it actually, for all of the metrics that we just introduced earlier, it can be added to the objective functions of the metric factorization and optimized. And we can see that it's as a regularization part of the objective function, the U we denote there. So that U can be replaced by any of the metrics that we described earlier. And for optimization, they actually use the smoother version, the Hilbert loss, which is a smoother version of the absolute square error, to actually have the conversions of the optimization. So this is the experimental results on the the synthetic data. So let me remind a little bit, right? This one, we saw the two stochastic blocks I showed earlier to actually generate the rating matrix. And in this experiment, they have 4 different sampling schemes with 400 users and 300 courses. For the uniform, this one, no bias. So this one, uniform means 400 users. Each group there, WWS, MS, and M, each one have 100 users. And the other one have like each group of the course have 800 each. And then the observation probability are 0.4 for all the block. So we actually have no bias in terms of observation. So the second one is a bias observation, meaning like the old bias, the metrics that I shown above are the bias that actually incur the observation bias. For the bias population, they actually have a different number of different number of users for each of the group. So this actually introduced the bias in population, the population imbalance that we discussed earlier. And the last one is a bow bias. So we actually have bow imbalance that compile together. So this is worst, the worst one. So for this synthetic data and the 4 sampling schemes, they did experiment with the standard metric factorization. And these are the results. I guess, not sure whether you can read the numbers there, but so the first one is the absolute error, whereas the other box are the values of different fairness metrics that they measure. And you can see that is as the uniform one are the less biased one. So we actually expect them to have the lowest score for different fairness metrics, and it's actually turned out that we actually have even the best error rate as well for that unbiased group. So for all the metrics that we showed there, except the last one, except the non-parity one, there's a strict order of the unfairness, meaning like the uniform data is the most fair, the bias observation is the next most fair, whereas the bias population is worse than the bias observation. And both bias combined actually have the most unfair recommendation. So this one can actually suggest some conclusion that the 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 imbalance of the population is actually worse than the observation. So it's okay to have not observed a lot of ratings from a certain group and observe more ratings from the other group. But if we have the imbalanced population, then it's actually more unfair. So the non-parity behaves a little bit different. So for this one, we see that the observation bias is actually very bad for this metric, the type metric. But the author argued that when you have the different, you have bias in observation, it's okay to expect the non-parity of the average, because for the group that you have more observation, you tend to have like higher rating, for example, than the others that you have less number of ratings. So it's okay to expect the high non-parity score when you have the bias in the observation. So this one is the table that they show the score for different metrics. The rows, right, are the objective function. Then you add in the metric that you want to minimize. And for each row, then you compare column wise, right? So you go by row, and then you compare column wise, and you see that looks like the value unfairness metric have the most. So you see the first the second column. So the first one is the original metric factorization without any fairness objective. The value is the one that add in the value unfairness objective, then actually have kind of good error as well, and good value unfairness as well as the underestimation, overestimation, where they also argue that the diagonal, the one that highlighted in the yellow color, are the one that actually adding the fairness objective. This actually being minimized as compared to the original metric factorization. So meaning adding to the metric unfairness can actually reduce the unfairness. So this, the authors say that it's up to the designer system. So which kind of fairness that you want to preserve in your system, that then you can actually focus on a particular type of unfairness metric. But this suggests that the value unfairness actually can also reduce the other unfairness as well. So the very last experiment, they actually experiment on the real world data set, the movie lens 1 million, very familiar. This one, to derive different group of user, they use the genre in the data set, and then they see which of the user gender have the very difference in the behavior, how they rate the different genre. And they actually 5 genres: the romance, action, sci-fi, musical, and crime. Those are the ones that have kind of bias, how the male and female user rate the movies. And this one, they also follow the same procedure, and they conduct an experiment and see how different unfairness metric can affect the results. And so just a couple of observation here. So optimizing each of the fairness metric also lead to the best performance on that particular metrics, which is trivial. In the synthetic, similar to the synthetic data, optimizing the value unfairness most decrease the, also actually have to decrease the under and overestimation, as we see on the synthetic data. And optimizing the non-parity again cause the increase or no change in the all the other unfairness metrics. So the non-parity is actually a very weak metric, and it actually doesn't have much on the other metrics. And that is the observation from this experiment. So let's come to the conclusion of this paper. So this paper presents various type of unfairness that can occur in collaborative filtering, and the 2 forms of data bias can lead to such unfairness, which they focus on the population imbalance and observation bias. And the traditional approach, the metric factorization, can be augmented to minimize these unfairness metrics. So a few future work can be considered as, so this one we only consider the bias in terms of items. We don't consider bias towards, we only consider the bias in terms of users, right? But we don't consider bias towards the items. So items also have different groups, and they also have different kind of bias that they have. And this method, they only focus on the experiment they did. The data set is quite dense. So this one, not sure whether this have the same observation when we generalize to more sparse data. And also the investigation in this paper is only for collaborative filtering, where for a lot of methods now use the other multimodal data to boost the recommended system. So how this unfairness matrix can be integrated to these source of models, and how it actually affect the outcomes of the recommendation. Okay, so that is all of this paper. Thank you.